Welcome back, focused learners. Today, we're tearing down the hidden, high-stakes engineering that keeps an electric vehicle from literally destroying itself the exact second you turn it on. In this explanator, we're diving deep into the fifth dimension, the system high-voltage execution and global safety layer. Specifically, we're breaking down the technical specs, root causes, and safety mechanisms behind the critical P0AE1 and P0A2B fault codes, the Precharge Contactor circuit anomalies. We're looking at the ultimate shield wall and exactly how it prevents the raw, destructive tsunami of an EV's own battery power from obliterating its internal systems.
So, let's start with a really high-stakes question. What actually happens if you take hundreds of volts from an EV battery pack and just instantly connect it to the rest of the car? Well, if you flip a switch without any protection, the results aren't just bad, they're immediate, and they are violently destructive.
The answer? Catastrophic inrush current. This massive, unrestrained wave of electricity slams right into the motor control unit, specifically the DC link capacitors, and instantly overloads and obliterates them. Without a precharge circuit acting as a sort of pressure valve to gently let the current flow in first, the hardware literally cannot survive the surge.
To understand exactly how engineers build an unbreakable shield wall against this, we're going to follow a 5-step engineering life cycle today. We'll cover 1. Lethal threat, 2. Double defense, 3. Design defense, 4. Zero defect manufacturing, and 5. Limit testing.
All right, Section 1, Lethal Threat and the Precharge Failure Analysis.
We are dealing with a severity 8 critical failure here. And keep in mind, this happens before the car even technically starts. There are 4 physical enemies relentlessly attacking our system. Sudden back-EMF voltage surges, extreme thermal breakdown of the resistor from rapid key cycles, physical short circuits or contactor welding on the load side, and finally, just basic wear and tear, like low-voltage harnesses degrading from vibration. Let's zero in on that first enemy for a second, back-EMF. When the precharge contactor coil disconnects, it creates a massive, self-induced kilovolt surge. Think of it like a high-voltage electrical whiplash. Without protection, this surge travels straight back to the battery management system's main board and permanently destroys the low-side driver IC. It just burns it out, meaning it can never trigger the coil again.
Moving right along to Section 2, Double Defense and System Architecture. To meet extreme automotive ASIL-D safety requirements, engineers rely on a brilliant hardware and software tag team. And it's all governed by one mathematical golden rule, the time constant, or tau, which equals R times C. That is the theoretical product of the precharge resistor value multiplied by the load bus capacitance. This elegant little equation dictates exactly how fast the voltage should safely rise.
And this really illustrates how incredibly tight the safety margins are. The software uses that math to monitor the voltage climb dynamically. Get this. The system has a razor-thin window of just 200 to 300 milliseconds. Within that literal fraction of a second, the software must see the bus voltage safely climb to at least 95% of the total battery voltage. But you know, what happens if it doesn't?
Well, if the voltage misses that 95% mark in that 300 millisecond window, the software drops the guillotine. It triggers the P0AE1 or P0A2B fault and completely, permanently locks out the vehicle. You are not going anywhere. Why? Because if it didn't lock you out, the main contactor would close on an uncharged bus, causing a catastrophic high-temperature welding of the contacts.
Let's get into Section 3, Design Defense, and the DFMEA strategy. This is where engineers proactively forge the physical shield against these threats. To defeat that massive back-EMF whiplash we talked about earlier, engineers add a flyback diode right across the precharge relay coil. This component acts as the ultimate shock absorber. When the coil disconnects, the diode perfectly clamps that destructive energy and safely loops it back on itself, keeping the surge totally away from our vulnerable smart ICs.
But stopping voltage surges is really only half the battle, right? We also have to stop the heat. We handle the immense heat of the resistor in 2 overlapping ways. On one side, we have the hardware margin. That's the brute force physical joule handling capability of the resistor itself. On the other side, we have the software model. This is an intelligent, real-time dynamic thermal estimation known as I²T. Essentially, the software continuously calculates exactly how hot the resistor is getting in real time.
And based on that dynamic heat tracking, the software enforces a super strict limit, a maximum of 3 precharge attempts per minute. If an impatient driver just sits there rapidly mashing the start button over and over, that precharge resistor will eventually absorb way too much heat and physically burn out. So once you hit attempt number 4 within a 60-second window, the system rigidly locks you out. It puts the resistor in a timeout to let it cool down.
Now for Section 4, Zero Defect Manufacturing and PFMEA Control.
You see, the most brilliant engineering design in the world literally means nothing if it's built incorrectly on the assembly line. On the manufacturing floor, the battle is relentless. The process includes 100% 3D automated optical inspection and solder paste inspection. This ensures that crucial flyback diode isn't installed backwards or cold soldered. They also run automated end-of-line voltage drop tests and even use infrared thermal imaging to validate heat dissipation.
Notice the incredibly strict tolerance here for the thermal paste holding the precharge resistor. The standard is 90% solid paste, with a strict maximum of 10% air bubbles, no more. If the air bubbles in that thermal interface material exceed 10%, those empty voids act as powerful thermal insulators. The heat gets trapped, and the resistor will catastrophically overheat and fail, even under completely normal everyday driving use.
Which brings us to Section 5, Limit Testing, or DVP&R Validation. This is the climax phase. It's where engineers absolutely torture test their own systems before a single car is ever sold to the public. Take the I2T thermal abuse test, for example. First, they literally bake the entire battery pack in an oven at 50 degrees Celsius. Second, they use a simulator to just spam key on and key off requests. Third, they track the software's calculated temperature to make sure it matches the physical temperature within a strict 10% margin. And fourth, they verify the system flawlessly triggers that lockout on the 4th start attempt.
And to prove that the flyback diode truly protects the internal chips from back-EMF, they run a massive switch cycle test. They force the coil to disconnect 10,000 times in rapid succession, hitting it with that kilovolt whiplash over and over again. After 10,000 strikes, the low-side driver chip has to still function perfectly, proving the diode has successfully absorbed every single blow.
They also use testing to prove their manufacturing rules are sound. When comparing thermal imaging results, Group A, which are the resistors with 10% air bubbles or less, safely peak at or below 120 degrees Celsius. But Groups B and C, which have higher bubble concentrations, they overheat massively. This physically proves exactly why that 10% bubble limit is completely non-negotiable and why automated rejection systems must intercept them on the line. And that brings us to the final, inescapable end-of-line test. Right before leaving the factory, the system does one last physical check. It measures the physical voltage slope and ensures it perfectly matches our mathematical golden rule, tau equals R times C. The deviation has to be within a tiny plus or minus 5% window. If it passes, a final checksum verification is written to the memory, proving the vehicle is actually safe to ship.
So as we wrap up this explainer, I want to leave you with this thought. Every single time an EV powers up silently and smoothly, an incredibly violent electrical tsunami is being perfectly tamed behind the scenes. It requires a meticulously engineered shield wall that spans mathematical design, flawless manufacturing, and truly punishing testing. So ask yourself, whether you're designing or just driving one of these machines, is your system's pressure valve truly strong enough to survive the tsunami? Think about that and keep learning.